Hello and welcome to today's Explainer. We are going to dive deep into the absolutely staggering mechanics and the breathtaking scale of our very own solar system. You know, when we talk about our cosmic neighborhood, it's really easy to just kind of picture a few scattered planets spinning around in a dark void. But the reality? Well, it's infinitely more complex and way more dynamic than that. We're actually looking at a massive system whose gravitational influence stretches out for nearly a whole light year. I mean, it reaches all the way to the Oort cloud, which is this giant spherical shell of icy debris completely surrounding everything we know. Understanding the intricate astrophysics at play here, everything from orbital mechanics to how planets evolve, is honestly what makes exploring our solar system such a thrilling intellectual adventure. So let's jump right in and start unpacking exactly how this incredible local neighborhood of ours actually operates.
Now, it's super common to conceptualize our place in space as this crowded, really busy system, but the sheer volume of absolute vacuum between all these celestial bodies is, well, it's completely staggering. We aren't just sitting in a neatly packed little row. When you stop and consider the vastness of our local cosmic neighborhood, the distances become almost impossible to intuitively grasp. Get this, you could literally fit every single other planet in our entire solar system side by side into the empty space just between the Earth and our moon. Yeah, seriously. And as scientists continually discover these highly compact exoplanetary systems orbiting distant stars, it really highlights just how incredibly spread out our own home system actually is. Grasping the sheer scale of emptiness is totally crucial. It's the first step to understanding the immense gravitational forces required to keep everything tethered together across billions of miles of dark, freezing vacuum.
So, what's the engine driving all of those massive gravitational forces? It is, of course, the Sun. But, describing it simply as just a central star dramatically undersells its absolute dominance over our system. The Sun accounts for a staggering 99.8% of all the mass in our entire solar system. 99.8%. That means everything else, every single planet, moon, asteroid, and comet is literally just leftover debris made from that tiny remaining fraction of a percent. And this massive sphere of churning plasma doesn't just hold us in orbit, it actively protects us. The Sun projects this huge magnetic bubble called the heliosphere, extending way out beyond the furthest planets. This unseen shield acts as a vital barrier, actively deflecting highly energetic, incredibly dangerous cosmic rays originating from deep interstellar space. Without the Sun's continuous, roaring output, our local neighborhood would be totally exposed to the harsh, destructive radiation of the wider galaxy.
Okay, so within that giant protective heliosphere, the primary hierarchy of our system is defined by just 8 major planetary bodies. And this very specific number, 8, is the result of millions of years of chaotic orbital mechanics and, well, much more recently, some rigorous scientific consensus. Back in 2006, the International Astronomical Union laid down a strict set of criteria to define what exactly constitutes a planet. The real game-changer rule was that a true planet must have enough gravitational dominance to completely clear its neighborhood of other debris in its orbit. And as you might remember, this is exactly why Pluto was reclassified as a dwarf planet, which locked in our core count at 8. These 8 survivors are the absolute heavyweights. They successfully navigated the violent, super chaotic early days of planetary migration, like what scientists call the Grand Tack hypothesis, and ultimately settled into the stable, continuous orbits we see today.
When we look at this complete inventory, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, a really distinct structural division jumps right out at you. It's driven by a boundary that astrophysicists called the frost line, or sometimes the snow line. Billions of years ago, during the formation of the solar nebula, the intense heat of the young sun dictated exactly where certain materials could even survive. Close to the Sun, only materials with super high melting points like metals and rocky silicates could stay solid. That's exactly why Mercury, Venus, Earth, and Mars formed as those dense, rocky terrestrial worlds. But if you travel outward past Mars and cross that critical frost line, temperatures dropped drastically enough for volatile compounds, things like water, ammonia, and methane, to actually condense into ice. This is what allowed Jupiter, Saturn, Uranus, and Neptune to accrete massive amounts of material, growing into the sprawling, swirling gas and ice giants that completely dominate the outer edges of our system.
Now, among those rocky inner worlds, Earth's unique ability to support life is usually just credited to its location in the circumstellar habitable zone, the Goldilocks zone, that precise distance where water can exist as a liquid because it's not too hot and not too cold. But being in the Goldilocks zone, that is only a fraction of the story. The true, unsung hero of our survival is Earth's active dynamo effect. Deep down, beneath our feet, there's a rotating, turbulent outer core of liquid iron, and it's generating a massive, invisible magnetosphere that completely envelops our planet. This magnetic shield aggressively deflects the solar wind, which is this continuous, highly destructive stream of charged particles blasting out from the sun. And we know exactly what happens if you don't have this shield. Scientists believe Mars actually once had a much thicker atmosphere and liquid water. But after its internal dynamo cooled down and basically stopped, the solar wind ruthlessly stripped its atmosphere away, leaving behind the desolate, totally irradiated landscape we see today.
The contrasts between these terrestrial worlds and the giant worlds out past the frost line present some of the absolute most extreme physical conditions imaginable. Just consider Jupiter for a second. It's a gas giant of such immense scale that it basically acts as the gravitational vacuum cleaner for our whole solar system, protecting the inner planets by deflecting rogue comets and asteroids away from us. To put its unbelievable size into perspective, you could pack roughly 1,300 Earths inside of it. 1,300! Now compare that staggering mass with Mercury. Mercury is a tiny, rocky little world locked in a brutal, punishing proximity to the Sun. And because Mercury lacks any significant atmosphere to distribute or hold on to heat, it experiences the most violent temperature fluctuations in the entire system. Its daytime side bakes at a scorching 800 degrees Fahrenheit. But on the dark, nighttime side, the temperature instantly plummets down to a freezing minus 290 degrees. It's just a perfect showcase of the wild, unyielding physics operating at opposite ends of our system.
And then, of course, there is Saturn. Saturn represents perhaps the most elegant, yet incredibly complex mechanics anywhere in the solar system. Its iconic ring system is literally a masterclass in orbital dynamics. While they might look like these smooth, solid, continuous bands from far away, they're actually made up of billions of individual pieces of water ice. And these chunks range in size from tiny little grains of dust all the way up to massive tumbling mountains of ice. But here is what is truly fascinating about Saturn's rings. Modern astrophysics suggests they are actually a relatively recent addition. They probably formed long after the planet itself, most likely from a completely shredded, icy moon. Furthermore, they are highly ephemeral. Recent observations have shown that Saturn is actively pulling its rings down into its own atmosphere through its magnetic fields. It's a wild phenomenon known as ring rain. So in the grand timescale of the cosmos, these magnificent rings might completely disappear in just a few 100 million years. Crazy, right?
So as we piece together all these incredible planetary dynamics, we have to scale our perspective outward one final time to grasp the absolute grandest mechanic of all, our macromotion. The entire solar system is not stationary, not at all. We are relentlessly hurtling through the Milky Way galaxy. The Sun is actively towing all 8 planets, the asteroid belts, and the whole Oort cloud along a trajectory toward the star Vega, heading in a direction known as the solar apex. And at the exact same time, this entire massive collection of ours is locked in a colossal orbit around Sagittarius A star, which is the supermassive black hole located at the very center of our galaxy. It takes our solar system roughly 225 to 250 million years to complete just one single orbit around it. We call that time frame a galactic year. To put that into perspective, this means the last time our planet was in its current position in the Milky Way, dinosaurs were literally just beginning to emerge on Earth.
Which leads us with one incredibly profound mathematical reality to try and wrap our heads around. Given our massive orbit around the galactic center, the entire solar system, including everyone here on Earth, is traveling at a mind-bending velocity of roughly 450,000 miles per hour. Let that sink in. We are on a continuous, high-speed voyage through the interstellar medium. Just consider this, in the 10 or so minutes it has taken us to walk through this explainer together today, you haven't just been sitting still. You have physically traveled tens of thousands of miles through the cosmos. It completely reframes how you think about your place in the universe, doesn't it? Well, I really hope you found these insights into our dynamic, incredibly fast-moving cosmic neighborhood as fascinating as I do. Keep looking up, stay curious about the astrophysics operating all around us, and I'll catch you in the next explainer.